So I guess I'll start off with the title. So welcome everyone to our presentation. And this presentation is going to cover what we'll be exploring, various cis and trans isomers of different molecules, and we'll be substituting the original substituents of those molecules with various other ones to observe various effects on the energies and of those molecules, essentially, right? So let's get right into it. So this is one of the things I'll be talking about. So the first thing one of the first things we learned in this program was about different computational methods and the benefits, regarding speed and accuracy associated with those methods. So the one that we used most often was one called B3LYP, which is a quantum-based computing method that uses, a quantum mechanical model that is very good at guessing the correlation of a molecule using a method called density functional theory, or DFT. And it provides a balance of accuracy and speed. We also investigated another quantum method called Hartree-Fock, which has the downside of not approximating the correlation of the energy of the molecule. And therefore, regarding quantum methods, we did choose to use B3LYP. The last method we were introduced to is a method called PM6 or PM7, which is a pre-programmed, which is a semi-empirical method, which is the fastest method, but it does unfortunately provide a loss of some accuracy, so we did not use that. And I will turn it over to Audrey to talk about submitting files in GaussView.
So to set up an input file, you first want to create your molecule in GaussView. And then when you go to Gaussian calculation setup, you want to choose your job type. So all of our calculations this time were optimization and frequency. And then also you want to do your method. And so for this example, I just used B3LYP. And then you also want to give your job a title. And then all the information that you actually want to be that wants to be copied can be found under the preview. And if you just want like a better view or edit the text there, you could go to the edit button and then just select all and copy this into the terminal where you paste it into your created input file. And then you just want to make sure you change the top line so that it looks like this, with the X obviously being the name of your file, and then you save your file. And Maggie will do analyzing this output file.
So after we create the input file, we can submit them. When it's submitted successfully, we can have a log file. So after we submit it, we push the Shift G, we can check for the normal termination. Normally, if we see there's a normal termination, we'll see we got the successfully calculated result. So by following the certain order, like command, like SF down, and all free energies, we can get the results for the electronic energy and the free energies.
Okay, so now I'll be talking about the compounds that I explored during this program. So there are basically three main compounds that I explored. The first of those is cis and trans 1,2-dichloroethene, which is essentially 2-butene with chlorine substituents, and as well as that one, cis and trans 1,2-dibromoethene, which are very similar in shape and behavior, as it turns out. The second two molecules I studied were some other interesting ones that I decided to investigate, called one is cis and trans diazine, and the other one is cis and trans dimethyldiazine, which are essentially cis and trans isomers with a nitrogen base rather than a carbon one, and I was curious about those behaviors as well. So here is a summary of the first research I did, which was discussing the effects of chlorine and bromine substituents on the HOMO-LUMO gap, the highest molecular orbital and the highest occupied molecular orbital and the lowest unoccupied molecular orbital. And I was curious if, replacing the CH3 groups of 2-butene with the chlorine and bromine respectively would cause the HOMO-LUMO gap of the molecules to increase relative to each other's, because halogens act as electron withdrawing groups, and also because of the fact that the gap between with the chlorine molecule should be larger than the gap with the bromine molecule if the calculation is correct. So these were the first diagrams of my molecules. The interactions primarily between Cl5 and Cl6. And the same is true of the dibromoethene. Again, very similar molecules. And here's a discussion of my results. So as you can see, first I'll talk about the HOMO-LUMO gap. For chlorine, it was around 0.33. And for bromine, it was 0.27. So those results were in accordance with my hypothesis there. But I also observed a very interesting phenomenon where in both cases, the free energy and electric energy difference of these molecules, but specifically the free energy, were very, very close. So you can see here, it was around negative 0.008. And the negative here signifies that the cis isomer was actually more stable than the trans. And for the free energy here, the difference was around 0.057. So again, similar, but relatively small difference here. And I thought, considering the fact that the cis for chlorine is greater than the trans, my main, hypothesis around why that was the case was because, I was thinking that repulsion forces between the chlorine were actually greater than whatever steric effects would be present there. So I think it was van der Waals forces for the chlorine that repel them apart, or that do not allow them to have the steric tension and found in the other molecules, was causing that difference here. And I thought that would be more severe for the chlorine than the bromine because the chlorine is more electronegative. But again, that's just my hypothesis here around why this data is the case here. So yeah, this is the first two molecules I studied, and now I'm moving on to the second, which is the cis and trans diazine and dimethyl-diazine. So second aspect of my research here. To find cis and trans isomers with high free energy differences. Again, tentative hypothesis here for cis and trans diazine was that nitrogen wants to be triple bonded to itself. So I was thinking that a molecule with a double nitrogen bond would lead to a decrease in the stability of both molecules. And with stability being correlated to free energy, I hypothesized that the instability of this nitrogen bond would make the cis and trans free energy differences increase or be more intense. And following up that hypothesis, I thought that adding methyl groups to further amplify steric effects in these molecules would further increase that energy difference because of the fact that, again, steric effects in the cis and trans butene were largely responsible for the difference in free energies. And I thought adding it to an already unstable molecule would further increase that difference. And in this case, these are my two molecules. Again, here is a hydrogen base, and here is a methyl replacement for that hydrogen. Trans-dimethyldiazine, again, with the switched orientation here. And my results did show this. In fact, they showed a pretty significant free energy difference between both molecules of around 5 kcals per mole. And comparing this to the initial of around 1 for 2-butene, I considered, well, this was a significant free energy difference. And I thought that, well, largely this is a result of the instability of the molecule. Following this, I observed a difference of around 4 or 3 kilojoules in this case that I attributed to steric strain, because when I added the methyl groups, well, the free energy difference increased to 9 compared to the original 6. And so I thought that the steric strain produced by the methyl groups was increasing the free energy difference by around 3 kcals per mole in this case. So yeah, those were the two molecules I studied, or the two classes of molecules. And I will turn it over to Audrey.
So these were the compounds I explored. So I mainly looked at, or the one factor I looked at was adding like a hydroxyl group or 2, because hydroxyl groups are they're kind of in a lot of like organic compounds, and it's like present a lot, including water too. So I started out by adding a hydroxyl group to the ends and then to the internal carbons, and then I decided to look at how 2 hydroxyl groups would affect molecules. So I did 2-butene-1-ol and then 2-butene-2-ol, and then the 2 others. And so the first one I did was 2-butene-1-ol. I just wanted to see how the hydroxyl group would affect. And so I thought it would lower the energy, but the biggest factor between the cis and trans isomers would still be steric effects. And so the trans molecule would have a lower energy than the cis, which my results did show. I think these were slightly, there was a slight increase compared to just 2-butene. So suggesting that like the hydroxyl group might have like amplified the steric effect slightly. And then I wanted to see how adding a hydroxyl group to the internal carbons would affect this, because sp2 carbons like to be more substituted because they'll become more stable. So I wanted to see if this would affect the results slightly. And so I thought the Z isomer would have a lower energy compared to the E isomer. And my results did show this. And so although my free energy difference did decrease from the previous one, so I was thinking maybe the substituted sp2 carbon did increase the stability, or both molecules had pretty similar steric effects, so that also could have affected that. And then so I wanted to see with 2 hydroxyl groups, and so I added them to the internal carbons first, because there they would be close enough, or possibly close enough to have a hydrogen bond occur. And so I thought the cis molecule this time would have a lower energy compared to the trans. And my results did show this. And so you could see there was a more significant difference between the cis and trans molecule, and the negative just shows that the cis molecule was more stable than trans. And I also measured the difference between the oxygen and the hydrogen, and this was the distance, which is within the distance that a hydrogen bond can't occur. And so I just wanted to test to make sure like this was probably one of the bigger factors affecting this. And so I added 2 hydroxyl groups to the terminal carbons, where they would be farther away apart and a less possibility of hydrogen bond forming. And so the numbers are back to being similar from the first 2 molecules I explored, where trans molecule had a lower energy compared to the cis molecule. And so I think I will be passing it on to Maggie.
So the 3 isomers I studied was acetyl, tetramethyl, and the cis and trans fat. The reason I choose them is because first, I want to see the hydroxyl group impact to the bond, and the second one I want to see like when the many methyl group add there, when the bonds get very crowded, what's going to happen. And the third one, I want to see, we always, in our real life, we always heard that trans fat is bad for our health. I want to find out why. So my hypothesis to the acetyl is the cis would have a lower energy compared to trans, because of the hydrogen bond affection between the oxygen 5 and the hydrogen 8. The hydrogen bond will stabilize the molecule, thus lower the energy.
Oh, you muted yourself.
Can you hear me now?
Yeah.
Yeah.
Okay. So I think the reason it's mute, maybe I hit the enter key. Okay, I'll be careful. So the result of the calculation supported my hypothesis, which is the okay. So the result of the comparison did not support my hypothesis, because although there's a, let me go back here. There's a hydrogen bond between oxygen 5 and hydrogen 8 maybe occur for the cis. However, the stereohydric, the position will have a higher impact to this compound. So if I use this molecule compound compared to Adrian's calculation, because her calculation for the butane to add to the hydroxyl group, there she does get the cis has a lower energy compared to trans. I think maybe because of the methyl group has an impact to this molecule. So she does get the cis has a lower energy compared to trans. But for my calculation, like we could go back to this one. So between the, can I go back to the slides? Or I cannot. Okay. So if you look at my molecule between the C1 and C3, the lower part there's only hydrogen H2 and H4, which have a lower impact to the, withdrawal power from the oxygen. That's caused the the cis still has a higher impact to the trans. So the second molecule I studied is tetramethylhexane. The hypothesis is this cis would have a much higher energy compared to trans because of the steric effect. If we look at the molecule, we can see both of the molecules are very crowded because of the methyl group impact. However, because of the position, like because the double bond is between C1 and C3, the trans isomer, they do have more space. And for the cis between C1 and 3, the molecule, they are adjacent, they are very crowded, they have a stronger compulsion to each other. So if we look at the result of the calculation does support my hypothesis, which means the cis, they have a much higher energy compared to trans in such situation. So cis and trans fat indicates the configuration of the molecule around the double bond. This cis molecule, this cis double bond causes the bond of a kink that prevents the fatty acids from packing tightly, keeping them liquid at room temperature. So my hypothesis is since cis fat cannot pack in tightly compared to the trans fat, we assume that cis fat has more entropy, thus has a higher free energy compared to the trans fat. So through comparison of the cis trans fat, we see the although the electronic energy difference between cis and trans fat, they are like a very similar. There does exist a difference between the cis and trans fat. That's why the trans fat, they can stay more closely, more tightly with each other. That's in our real life. The trans fat, they stay in a solid status. That's why they are more stable. Could be like a stick in our artery, which cause some heart problems. So this is what we learned beyond the computational chemistry. We collaborate, work together as a research team, and we learn from each other. Also, we thankful for all the invited lecture speakers because they showed us all kinds of possibilities. Also, our major career goal has some adjustment after the camp. Like me, after this study, I found out it's very important to take more courses in computer science and calculus and physics that will help me to understand much more in the computational chemistry. And I'll let Audrey and Watt talk about their takeaway.
I guess for me, one of them was affecting like what I want to do beyond, or like what I want to do in school and after. And so I'm currently like a general biology major, but I've already been debating on double majoring in either chemistry or biochemistry. But after this, I think I also maybe want to change my major to like bioinformatics or something, because I found this really fun, and also it has a lot of applications with like stuff that I'm interested in, like genetics and like toxicology and stuff. And so this was a really eye-opening opportunity for me.
Yeah, could I add something for the last one? Oh,
please.
Yeah, for me, I think it showed me, the concrete nature of research is like, I've done research in the past, but taking an idea from your head and putting it into real life is definitely, this definitely gave me a lot of experience in that area and showed me sort of the similarities about what you're thinking about, how it's different, in a real life setting. And that, that skill, going forward definitely helps gives me sort of a concrete basis to what research is. I think it's definitely opened my mind to, what that is, and how the forms it can take and all the different, directions that can go in real life versus just thinking about an idea, implementing it with tools and learning about it that way. definitely gave me some new insights into that. All right.
This is really exciting. I don't know if I have exactly the right words for it, but it's really inspiring to see all of, I mean, how much you all have grown in 6 weeks. Like for me, it has, totally flown by, and I've just been blown away about how fast you've learned, and all of you, right? And on how to teach even better. I think maybe Leticia and Christian may comment on that as well. But it's really been a fantastic opportunity and growing experience, I think, for me personally. So I really thank all of you, both mentors and mentees, for participating in this program.
Yeah, I mentioned it yesterday, but also gonna mention today, which was like a really great experience to have you guys. Very similar what Stephen said. It was like I learned a lot how to improve, like how to teach, and also I learned a lot with you guys, like with your questions, like made me really improve. And I was like so happy with the project, how you guys like digging to actually do the research, ask like a lot of questions about this makes sense, this not. So I really enjoyed time with you.
Same here. Like I'm the newest member of the group, so it's kind of nice to be able to like teach the things that other people have taught me in the few months I've been here. So it's always like also nice to see you guys grow, and just like overall just get the hang of like how to submit jobs and what to look for, like how to troubleshoot. So it's always been like, it was really nice to see all of you guys grow a lot, like Steven says, in this short 6 weeks. So yeah.
So do we have any scientific questions for the presenters? Okay, I can start. So thinking back to the molecule with the dihydroxyl molecule, that I think that was Audrey's, if I remember right. So it was the ethylene with the two OH groups on them, right?
The one with the methyl groups at the end, or no?
No, the one with that one, yeah. Oh, back, I think, yeah. So I guess, were you surprised that you could find a molecule that had a lower energy cis?
A little bit.
Okay, and how about the others? Were you all surprised by that?
Yeah, it's really unpredictable, I found. Yeah, definitely.
Yeah.
Actually,
Yes.
I still have a doubt with this result.
Please.
It's unbelievable, you see, like it's anti our like instinct.
Intuition, yeah.
Intuition, yes. That's why I said, I had the the two carbon with the hydroxy group, because as in this one, she has a methyl group underneath that may balance or take away some of the balancing molecules. So still I cannot believe it. I would doubt if the machine is wrong.
Yeah.
Yeah.
Yeah, so it's true. I think actually what you're saying, that these methyl groups could, like if those methyls were hydrogens instead of methyls, do you think the reaction energy would be more negative or more positive, or the same?
But I did exactly. Oh yeah, I did this different molecule. Yeah, if it's hydrogen, definitely it's going to be still the cis, as because I did the calculation. I think the cis will still have a higher energy compared to the trans.
Okay. Well, maybe something worth checking. But yeah, that's cool. And then the other question I had was with Wyatt. So you showed a gap, a HOMO-LUMO gap in your slides. Can you go to that slide? Yeah, so is that the 0.33? Is that energy in kcals per mole or electron volts, or what are the units for that one?
I think this one's just a raw number, actually.
Oh, okay, like the Hartrees.
Yes,
Okay.
yeah, it's the output.
Okay, and then I might have missed it, but what does that mean to you? What did the HOMO-LUMO gap help you to understand about this?
I was just trying to see if the halogens would have the effect that they normally do, which is having that decrease, that the chlorine would be larger than the bromine. That was all. I was trying to verify that. But then there's an interesting thing that happened where the chlorine was actually more stable than the trans. And I was, yeah, I was thinking, like, you know, the forces between those two chlorines were somehow there's not a steric effect of the cis. I was thinking there was a repulsion between them. That was interesting to me. I didn't expect that.
Yeah, that is surprising. Yeah, I think, yeah, we had talked about this molecule, the dichloro, and I would have thought, I mean, actually, when Wyatt first brought this to me, I thought that, you know, maybe, you know, this either both the cis had been computed twice or the trans had been computed twice, and that's why they're so close, right? Mine this 0.008 kcals, which basically means the same, 0. But there's not. So I guess, yeah, that means that those chlorines are not interacting with each other, and that, you know, with steric repulsion that you might think that they are, this kind of electrostatic repulsion. So yeah, definitely.
I looked into it a little bit, like in terms of like reading. It's these molecules with they're interesting. There's not really, there's definitely not as much of a difference with the chlorine.
Yeah, not something I'd expect. So that's definitely an interesting. That might be a good like quiz problem or something to try in one of my classes in the future. Have them try and guess and maybe do some calculations on it. They'd be surprised. So thanks for that. So any questions, scientific questions from Leticia or Christian? Maybe not. Okay. Cool. Yeah. Well, I think the presentation was really, really well done. I like how I mean, it's kind of emblematic of how you all work together this summer, right? It like kind of came together. I think the presentation was really smooth, and the slides look nice too, which is always kind of a thing for me. So yeah, I think this was really great. So I think we'll send out a survey in the next couple days, just of, for you to reflect on your experience with this and giving us ways to, improve this. Like I've mentioned before, this is the first of 5 years at least where we'll be doing this kind of program. And this year, while we started with 3 students, I think, next year we'll have, 5 or 6. And, also the grad students and the mentors will be a little more experienced too. So maybe they can have 2 students each and kind of grow in that direction. So any feedback you have, it'll be anonymous. So don't hold back. If there's anything you think, we can improve, we're all ears. And if there's anything you think went really well, do let us know as well, so we can keep doing that.